So when I made the previous video, I thought that I'll actually stop at that point, but then I decided, let me give you a few more details about the space habitation where someday in the future most of humanity is going to live. And even though the space habitation design, which is in my book, is my design, and this was mainly, I thought of it like I would lie at night trying to fall asleep, and this was before I started listening to audiobooks, and then I would just like try to think of something to fall asleep, and then I would think of the space habitation and how one could build that habitation. Now, of course, later I came across space habitations which two people are especially notable for having pioneered the idea. They are Bernal and Gerard O'Neill. So let's take a look at them. This is Gerard O'Neill. He was a professor of physics, and this is Bernal. So acknowledgements to these visionaries who pioneered these ideas. Okay, so getting back to my design, this was the habitation. These are, what you see over here are these concentric circles with various layers, and the most important layer to start with is, of course, the other agricultural layers, followed by the habitation layers. So in the middle of it, it's all air, and then you have this, the tube, which is the innermost tube, is where the humans will live, and then you have successive agricultural layers. There will be actually 5 agricultural layers. So based on the calculations, which I'll provide, some of the calculations, not all. For all the calculations, you need the book. For some of the the calculations will say that the mass of this habitation, which has a population of 50,000, the mass is going to be 1.42 trillion kilograms. The diameter, I've just set it as a mile. So you're living here, and then you're looking up, and your, what do you call that, upstairs neighbor, that's the person living at the other end of the tube. So what I mean to say is that suppose you're like living over here, and then there's somebody living there. So you look up and you see their house a mile away from you. You should not feel claustrophobic. It's like being in this gigantic mall with a 1 mile high ceiling. That's what it'll be like, and it'll be all very green and pretty, and there'll be water bodies, there'll be parks, there'll be flower beds, there'll be beaches. It's just going to be fantastic, and it's going to be about 11.3 kilometers long. And where does actually that number, what is the major determinant of that number, 11.3 kilometers? It's essentially the amount of agricultural land that you'll need to provide sufficient food for the population of 50,000. And I'll come back to that later. And that agricultural land will be, you need some like topsoil, and lunar regolith is a nice candidate. The moon is not too far away, can be easily mined using electromagnetic railguns. And you can also grow food in water. And NASA has done some experiments about it. Okay, so let's get to like the details of the needed agricultural land. And Earth's population is currently 7.85 billion. So the agricultural area per human is about 5,670 meters square. You have to get the estimate of how much of the land on Earth is used for agriculture. So based on that, we get to 5,670 meters square. And if with that as the per capita requirement, we come up that the required agricultural area in the space habitation will be 284 million meters square. And we assume that the topsoil depth of 1.5 meters will be enough to provide the growing surface needed for crops and other food. Okay, now remember there are these 5 of these layers, right? And the question is, these layers actually they solve 2 problems, 2 very important problems. One is, they produce food, and the second is that they protect the inhabitants who live in the inner tube from radiation. Radiation is a huge problem in space. And you think of like going and living on Mars. Unfortunately, you'll have to live under a very thick roof if you want to live on another planet, unless it has the features of Earth, which is the atmosphere and the magnetosphere, which protect us from radiation. So how much shielding do we need? Well, according to NASA, we need about 11,000 kilograms per meter square of shielding, and this is from a book by Marotta and Globus. It's a very good book. So we have now stacked 5 agricultural layers, each of depth 1.5 meters, and so how much shielding does it produce? Well, these 5 layers will produce a shielding of 12,000 kilograms per meter square, which exceeds NASA's requirements. Okay. So these agricultural layers will provide sufficient shielding. So now we have land for agriculture. So what is the other thing we need for agriculture? We need energy, or free energy as it is called. And this energy is going to be used for grow lights, which will provide the energy necessary for photosynthesis by the plants. And we have an estimate, we can make an estimate of how much energy will be needed, because grow lights are commercially popular. So just I took some numbers that I found from some commercial vendors, and the final number I came up with is that for these 284 million meters square of agricultural land, the amount of energy that will be needed will be 15.98 gigawatts. So, energy is needed for agriculture. That's the main need for energy. That's also needed for other things like light, or if you have some transport and stuff like that. So I'm just going to assume that the energy needed for other purposes is what the average US citizen consumes currently, which is about 3.7 kilowatt. And then you multiply that by 50,000 inhabitants in the space habitation, and you end up with the total amount of energy to be 16.2 gigawatts. Now, the solar panels I had calculated earlier, the the solar panels are going to provide about 24.7 gigawatts, but we are going to assume that, well, that's the energy incident on the solar panels, which is about 1368 watts per meter square on Earth orbit. So not like on the surface of Earth, because a lot of that energy is lost when it travels through the atmosphere, when the sunlight travels through the atmosphere. So this is at the Earth orbit without any interference by any atmosphere. So that is about 24.7 gigawatts, but we can't assume 100% efficiency for the solar panels, so we're just going to assume, like, let's say 50% efficiency. So with 50% efficiency, the solar panels are going to provide us with 12.35 gigawatts of energy for the space habitation, which is less than what we have calculated. Our need was about 16.2. Now, there are a couple of things you can do to make up this shortfall. One is that a lot of the energy which is used for agriculture can again be recovered as biofuels. Or you can simply extend the solar panels, like wings outside the space habitation. So the bottom line is that energy is not a problem. You have plentiful energy in space. The issues really are producing the gravity, providing radiation shielding, how to set up the agriculture, and of course a luxurious life which will which will motivate people to leave Earth and go to space, because the life which the average person can have in space is going to be much more luxurious than what we have on Earth. So, speaking about agriculture and energy, of course, this is something which the technology still needs to be developed. And very good work is being done by the European Space Agency. They have this project called the MELISA project, where what they have is an enclosed ecosystem, an ecosystem which is closed off from the rest of the world, but the only input is energy, and which is going to be similar to what you have in a space habitation. The space habitation is going to be isolated from the rest of the universe, or it is isolated in the sense that unless you want to travel outside, but in general, it'll be an enclosed ecosystem. And in that, you're going to get an input of energy from the solar panels. Similarly, MELISA is this project which is on Earth itself. It has been closed off from the rest of the universe. And what they have is that they have some mammals in there, which are rats, okay? And then they have a variety of plants and bacteria, and also just to make it provide everything that is needed in an ecosystem. So essentially, you take the energy and you produce food, and the food is eaten, and then it decomposes, and then it's fed back as fertilizer for the plants, and then the process repeats itself. So you need the one which you want to provide for is the other mammals, like humans. Okay, so the humans are also mammals like rats, so they have some rats living in there. So the idea is that how can we provide for mammals, which are a higher level of organism in a closed ecosystem? How do we provide them food? How do we take care of the, their, whatever they produce after eating food and drinking water, how to take care of that, and then you have it being decomposed by bacteria and being fed back to the plants. And all this process needs energy, and as we shall see later in the book, the idea is that you're maintaining organization. You are preventing disorder from coming in. And in a universe of constantly increasing entropy, you need an outside input source to make it work. Okay, so I think this is probably all I'm going to talk about as far as the design goes, but just one thing about the mass needed for this space habitation, and the mass needed turns out to be 1.42 trillion kilograms. Now this mass is actually double the mass needed, because this is like a safety margin. A lot of time you're going to find mass in the form that you can't really use. Maybe there'll just be an excess of hydrogen. You can't use hydrogen for building structures unless you kind of combine it with carbon and you make it into a hydrocarbon, which you can convert into plastic. But anyway, so that's something I do not go into the details, because that is really technology to be developed. But recognizing that we may not have exactly what we need in terms of raw materials, what I have done instead is I've just said that let's give a safety margin of 100%. Let's just say that the amount of mass needed will be 100% more than what is suggested by these calculations. And that doubled mass turns out to be 1.42 trillion kilograms for a space habitation which houses 50,000 humans. So that's a very important number, because that number is going to tell us what exactly the sustainable carrying capacity of space is, what the sustainable carrying capacity of our solar system is, what the sustainable carrying capacity of our galaxy is, and finally the sustainable carrying capacity of all galaxies in the universe. Okay, so that's a very important number. And with that, I am going to end this video. And be sure that if you want the details, there are a lot more details, like how do you get the gravity that you want, stuff like that. So if you want, do buy the book. Lots of details in there which have been worked out. It's I've not really left anything important out. This is not, like I say, it's not science fiction. This is just science.